Alright guys, today we're talking about geometric construction. Okay? Geometric construction. So far, you guys have done single view drawings and you've learned how to put height and width in. We haven't learned depth yet, but we will in multi-view drawing. But what we're going to do today is show you how to apply geometric concepts to your drawings, because not everything can we do with just the tools at hand. We have to understand how to develop these and the geometry behind it. Those geometric concepts that you're learning, you can apply those in drawing, and you can actually, there's a ton of math problems that I figure out just by doing a drawing rather than spend 45 minutes working out a trig problem. Okay, because I can draw it in about a minute and figure out what I need to figure out rather than doing a bunch of math. Nothing wrong with doing a bunch of math, but sometimes doing a drawing can be a little bit easier, especially with solid modeling programs. You can figure out area, all kinds of things. You could subtract area of one circle from the area of another circle at a certain tangent point, and just all kinds of things that you would normally take some either trig or calculus, triangulation methods to figure out the problem. We're going to go over some definitions of what this stuff means as we draw it. This is not something that's a formal drawing. This is actually practice for you, so whenever you get into the formal drawing, you'll be able to know how to do it. So I guarantee you, when you go out and you become an engineer, then there's going to be lots and lots of people that don't understand these concepts, because there's not hardly anybody that teaches it anymore. People gloss over board drawing. Most of the time, they don't even do board drawing in curriculums anymore. So therefore, they lose the concept of all this geometric construction. Okay? Just like when you guys were figuring out the width of some of those drawings, you had to add in the radius. And for you to do that, you have to understand the radius is the distance from the center all the way to the edge, no matter where you are on that circle. Well, there's a whole lot more to it than just that radius aspect of it. So we're going to start by looking at some of the geometric construction and what they mean. So a point, if we're talking about something in geometry, a point is a theoretical exact point in space. What's the significance of a point? When you get into SolidWorks, it'll be very significant, because it's actually a location. You're defining something when you get a point. But what's the definition of line? The distance between 2 points, right? And then if we have parallel lines, what's that significance? What does parallel mean? They're always equal distance apart, and they never intersect or touch. Okay, that helps you, because when you're creating parallel lines, we can create a parallel line using one radius and just drawing 2 arcs and making that parallel. All right, what is the definition of perpendicular? Do the lines intersect when they're perpendicular? So at what angle will they intersect? At 90 degrees. So perpendicular means they're exactly at 90 degrees to one another. Horizontal, you guys, I've been using that, so hopefully you've understood what I've been saying. So horizontal means it goes right to left. Vertical means it goes up and down. An arc, when we talk about an arc, we describe an arc with a radius. And an arc is just a portion of a circle. Okay, and your free curves, what can we make a free curve with? What instrument? The French curve, right? If we don't have like a standard radius that we're following, or if we have various radii that we're following along the line, the French curve is a good tool to use. Okay, so we see examples of all of those things right here. And you're going to need to know the definition of all those things. You need to know what it means. And we're going to apply those in just a minute. So some other things we need to know about is angles. right? A complete circle has how many degrees? 360. And we can break that down. Half a circle has how many degrees?
180.
Okay. And then a right angle has how many degrees?
90.
If it's less than 90, it's called an acute angle. And always remember that because babies are cute. So if they're young, then they're acute. They're lower than 90. Okay. And obtuse is greater than 90s. All right. Complementary angles add up to be 90. Supplementary angles add up to be 180. So you guys, if you don't know these things, then you need to be writing them down in your notes. It's very important. When we deal with things like arrays, and I'm going to show you how to do an array in AutoCAD, you need to know how many degrees is in a circle and how far apart each number of those entities are going to be. Knowing this stuff helps us understand polar coordinates. It helps us to understand if the angle is coming from the horizontal or the vertical. Because when we're on the board, when we're doing board drawings, it's easy to flip your triangle to where you need it, right? You don't really even have to understand what the degree amount is as long as you can flip that triangle to make it fit. But in AutoCAD, you actually have to understand polar coordinates. You have to know where it's coming from and what angle it is. And when you get into actually manufacturing these parts and you write G-code so the machine knows where to go, you have to input it in the proper angles or it's not going to do correct, or it's not going to be correct. All right, so know your angles. Know what a right angle is. Know what an acute angle is, obtuse, complementary, and supplementary angles. Then we're looking at our triangles. Equilateral triangle, they are equal on all sides. Okay? That's important. If they're equal on all sides, then what are their angles? Their angles are 60 degrees, and the angles are equal, and the sides are equal. So an equilateral triangle is also a regular polygon. So you might not know this, and you need to write this down. A regular polygon is a multi-sided shape that has all lines equal and all angles equal. Equal lines, that means the length of the sides are equal and the angles are equal. That's a big deal. You need to understand that because when you're creating geometry, if it's not a regular polygon, then it's not going to follow all the rules. A regular polygon has all sides equal and all angles equal. Powerful stuff. When you get into calculus and you start doing triangulation methods, then you're going to be able to understand it a little bit better. And you can always work off of the equations because we know that they are true on regular polygons. So an equilateral triangle, because it's equal on all sides, is a regular polygon. And all the angles are equal, and those angles are 60 degrees. Because how many angles, or what's the total sum of angles in a triangle? 180. What's the total sum of angles in a circle? 360. Okay, now isosceles triangle has two sides that are equal and two angles that are equal. So isosceles, and you can see how it's spelled there. Two angles equal and two sides equal. A scalene triangle, there are no sides equal and no angles equal. And then we have our right triangle. That means one of the angles is 90 degrees. What's special about a right triangle? If one of the angles is 90 degrees, what can we count on?
The other angle is 45.
It's not necessarily 45. It can be 45.
If they add up to 90.
If we have a 90-degree angle in our triangle, we can use what theorem to apply? The Pythagorean theorem. Okay? So we can only use the Pythagorean theorem on a right triangle. A squared plus B squared equals C squared. Okay? And you're going to apply that a whole lot in your life. All right? So right triangles that have a 90-degree angle and follow the rules of the Pythagorean theorem. A squared plus B squared equals C squared. That's what we need to know for those triangles. And then they have this little arrow at the top here that's pointing to what? What's that called? A vertex. So if it is a 2D object, like this triangle, and it comes together, if your angle comes together at a point, that's called a vertex. We didn't talk about quadrants of a circle just yet, but we will. But if it's a 3D object, say like a cone that comes together at a point, what is that point called? It's like a vertex, but since it's a 3D object, we call that an apex. So where 2 points come together from an angle, that's a vertex on a 2D object. The same point on a 3D object would be called an apex. Knowing this stuff is going to make you a very, very powerful designer. Okay, when you get into statics and strengths and materials, you'll learn that the triangular shape is the one that has the most strength. So a lot of bridges that you see, a lot of structures that you see have triangular shapes because it distributes the weight evenly and it's stronger, it won't collapse in. All right, then we get down to parallelograms. So parallelograms just mean that the sides are parallel. So if we have a square, what's the significance of a square? All sides are equal. And that means all angles are equal. The rectangle, opposite sides are equal, and all angles are equal. Rhombus, we have equal sides, and the opposite sides are parallel. So a square, opposite sides are parallel. Rectangle, they're parallel. Rhombus, the opposite sides are parallel. And a rhomboid, the opposite sides are parallel. So those are all known as parallelograms. So on this one, you know, parallelograms, there's 4 different kinds: square, rectangle, rhombus, and rhomboid. And if the opposite sides are parallel and equal, then the angles, the opposite angles have to be equal, right? If we look at the rhomboid here, this angle is going to be equal with this angle, and vice versa. The opposite angles are going to be equal. So which one of these is a regular polygon? Out of those 4 parallelograms, which one of them is a regular polygon?
Square.
The square is the only one that's a regular polygon, because that's where all sides are equal and all angles are equal. And then we have 2 more 4-sided objects. All of these were 4-sided objects, but the first 4 were the only ones that were parallelograms. And a trapezoid is a 4-sided object. but it is not a parallelogram and it's not a regular polygon. Two sides are parallel, but then you don't necessarily have to have any equal angles on that or any equal sides. Same thing about the trapezium. No sides are parallel and no angles have to be equal. There's different methods that we have to use to create this geometry if we have polygons that are not regular polygons. Okay, and then we get into how to create those polygons. So I want you guys to write this down. Very important. And AutoCAD actually prompts you for your decision on this whenever you make a polygon. So if the polygon is a regular polygon, we can make what's called a construction circle to create this polygon. Okay? Because a regular polygon can always be made within a construction circle. If you make the polygon inside the construction circle, like you see here, then it's called inscribe. You need to know that. Okay, every software that you're going to use is going to ask you, do you want to inscribe or circumscribe? You need to know the difference. Because if you choose the wrong one, you're not going to make it the correct size. And I have a couple drawings that purposely try to trick you because you have to make that choice and you have to make the right choice. So if it's inside the construction circle, we call that inscribe. If it's made on the outside of the construction circle, we call that circumscribe, like you see here in B. So you see the construction circle. So the distance across the flats of this square is equal to what? How do we define a circle? We need to know two things about a circle, right? Or a hole. What are those two things? Anybody remember? We need to know how big it is and where it is. So how do we know the distance across the sides of this square? What's that equal to? The diameter of the circle, right? Because the lines of the square are made tangent to that circle. What does tangent mean? Tangent means it's touching it at just one point. Okay? So something that's tangent to a circle means it's touching at just one point. So we're drawing these lines of the square tangent to the circle at the top and the bottom and from right to left. So the distance across the flats of that square is the same as the diameter of the circle. Okay, so when we have to create this construction geometry, that's how we know how to create it. Right? So inscribe, polygon is made inside the circle. Circumscribe, it's made outside of the circle. And then we have a 5-sided object, which is called what? Pentagon. 9-sided, you'll see over here on the side. That's probably hard to read for you guys. That's a nonagon. 10 is decagon. And then 12 goes into dodecagon. So you need to know what those are. You need to know, especially octagon and hexagon. There's a lot of structures out there that use, even a pentagon, those types of angles and regular polygons to enhance the architecture. Okay, so how do you think those are laid out? Same methods that we are going to do on the board here in a second. They just do them on a larger scale. So know what a regular polygon is. These are examples of regular polygon. All sides are equal, all angles are equal. And then we get into circles. So the circumference is what? What's the definition of circumference? It's the distance outside of the circle. Why would we need to know that in drawing? Because I've already told you, you only need to know two things about a circle: where it is and how big it is, right? But what if you're doing some pattern development? Let's say that you have a funnel that you need to make, or you need to make a cone, and you need to make it out of sheet metal, so you've got to cut the sheet metal and bend it into a cone shape. Are you going to need to know the circumference of that circle then? Yes, you will, because you have to lay out the line. We have to stretch this out, so the circumference, if we took this circle and broke it and stretched it out in a straight line, the circumference is the distance of that circle. Okay? So there are many, many applications where you need to know and understand what circumference is. We know what a diameter is, and the key to the definition for diameter is the distance across the circle through the center. If you don't say through the center, then it could be a chord, it could be a segment, it could be, quadrant or sector. So there's that significance of through the center. And then we know the radius is the distance from the center anywhere on the outside. Let's look at quadrant a little more. When you're in AutoCAD, it will allow you to snap to quadrant. So a quadrant is any of those 4 points at the 90-degree marks along that circle. Tangent, here's an example of a line that is tangent to a circle. And guess what, guys? There's all kinds of symbols that you're going to need to know in engineering and design. So if we took away this line, this secant line right here, then that's actually the symbol for tangent, a circle with a line that's tangent to it. So when you're looking at these symbols, if you know what the definition is, you can kind of understand what the symbol means and how it would apply just because you've seen it before. And then we have concentric circles. What does concentric mean? They share the same center, right? That's very important, and we've understood now, since we've done a few drawings, how important that is. So eccentric circles share the same center. When you get into SolidWorks and you start creating assemblies, you have to mate objects together for the assembly, and concentric is a very common mate. Tangent, common mate. Okay? Eccentric circles mean that they're overlapping, but they do not share the same center. So an example of this might be a gearbox. You might have a gear, a pinion within a larger gear on the outside. And so the most important words that you need to take from here, all of it's important, but you need to know the circumference, you need to know what a quadrant is, diameter, radius, tangent, you need to know what that looks like and what that means, concentric. You're going to use all of these things when you're drawing. And then if we flip over, these are examples of the 3D shapes. When you get into solid modeling, you're actually modeling 3D shapes and just adding them together and subtracting them and intersecting them. There's 3 basic modeling operations: add, subtract, and intersect. So you have to understand, if I put 2 3D models or 3D prisms together, then I'm actually creating a shape. I'm creating a solid model. So you need to know what these are called, what they look like. Okay, and we talked about the tip is no longer a vertex, it's called an apex. There's another word that you're going to hear in design. When it's cut off at an angle like this, like the top of the pyramidal prism here, the right square, then that's called truncated. Truncated means it's cut off at an angle. Here's a truncated cone. Prism, and you have different kinds. This would be right square, right rectangular, right triangular. Right, and then you have a circle that if you give the circle a depth, it's called a cylinder. Okay, and And then you have your pyramidal prisms. You have your cones, a sphere, a torus, an ellipsoid. So this is a horizontal ellipsoid, which is called oblate, and a prolate ellipsoid, which is like a vertical. So those are your definitions for geometric construction. Now I'm going to take you through the process, and we'll do this together. But I want to take you through the process of doing things like bisecting a line. What does bisect mean? Cut in half, 2 equal parts. Okay, bi means 2. So we're taking a line and dividing it in 2 equal parts. All right. So the first thing that we're going to do is bisect a line. So somewhere on your paper, and we're going to do several things on this paper, so don't make it real big and don't make it in the middle. This is, like I said, practice for the real deal. So somewhere, like in the top left corner, I want you to make a line. You don't even have to measure it. Just make it, eyeball it, make it a couple inches like you see mine. So we're not measuring it, you're just eyeballing it, making it a couple inches long like you see on my screen. Okay? So because we did not measure this line, if we want to bisect it, we would have to measure it first and divide it by 2 and that kind of thing. We don't need to do that. We can use geometric construction to create a bisecting point for this line. So you're going to take your compass and you're going to put your needle point on the very end of the line on this side, and you're going to wheel your compass out to just a little bit past the halfway point on that line. So we can kind of eyeball it and see that it's a little bit past the halfway point. Just like you see on, I'm doing on the screen. Okay, and you're going to have to follow along, so make sure you're staying focused. So needle point on one side, wheel the compass out. We're not putting any kind of measurements or anything. We're not using our scale at all. But once you get it wheeled out past the halfway mark, then you're going to put the compass at the end point and strike an arc. So you can strike it all the way like a half of a circle here. Do not change your compass. Don't hit the wheel on your compass because you want the exact same distance on the other side. So without changing our compass at all, we're just going to flip it over and put the needle point on the other side at that end point. Make sure you get the exact end point, and then you'll strike another arc. And you end up having something that looks like this. So we didn't even have to create this geometry with our straight edge as far as making it parallel with the edges of our paper. We just drew a line. We didn't know what angle it was drawn at. We weren't real accurate other than we know it's a straight line. Then we wheeled our compass out halfway or a little over halfway and struck 2 arcs, one from each side. Now we're going to take our straight edge, because now we have 2 points, right? We have a point here and a point here because we have intersecting lines that make that point. And we can use our straight edge and put it tangent to those points and then draw that line. And that line bisects the other line. So now we have two equal sides. So we bisected this line. So I'm writing what I'm doing on each of these, which is probably a good idea for you guys too. That way when you look back at your notes, you'll understand what we did. We bisected this line, meaning we split it into two equal parts. We had no idea what the measurement of the line was. We didn't need to know. We didn't even know what the size of our arcs were. That's the power of geometry. Now we can also bisect a line doing something different, but if we do it this way, we do have to make sure that we're horizontal, so you're going to have to use your straight edge for this. So I'm going to bring my straight edge up to about right here. This is fine. So your horizontal straight edge, you'll have to use it. And then just, make another line about the same size as the one before. Mine's actually a little bit bigger. I'll probably go off the page, so let me erase some of that. So I made this with my horizontal straight edge. And because I did that, because I know that it is at that horizontal line and it's at that 180 degrees, I can use my 45 triangle. So the angle 45 is very significant. I'll stop talking. The angle 45 is very significant because it means that we're going to have equal sides on both sides. So something like a chamfer, if it has a distance by a 45-degree angle, that means the distance is going to be the same on both sides. So we can use our 45-degree triangle and we can put it up against our straight edge. And then we can make it tangent to the endpoint. Okay? So I'm putting it against my straight edge, making it tangent to the endpoint, and then I can make a line. So I made a line that was at 45 degrees tangent to my endpoint. I'll do the same thing on the other side. So I'm just sliding the triangle using the other side of it. It's still flush with my straight edge. Making it tangent to that endpoint. And where they meet at the top, I have this point. Now I don't have another point at the bottom. I could do it. I can flip my triangle over and do it at the bottom, but I don't need to because now I can take a straight edge, make it flush with my horizontal edge, and make it tangent to that point. And now I have bisected that line using my 45-degree triangle. I still didn't measure anything, but I used the 45-degree angle to my advantage and found the midpoint and just made my line straight down. So this is bisecting a line using a compass. And this is bisecting a line using 45-degree triangle. So I used that 45-degree angle to my advantage. Anybody ever heard of a miter line or a miter joint or a miter saw? Okay, that just means 45 degrees. If you have a miter joint, they meet at 45 degrees and they automatically meet up because they're going to be the same size. So we've learned how to bisect a line. Now we're going to learn how to bisect an angle. So what was an acute angle?
There's a little baby.
It was the baby angle, so it was less than 90 degrees. So on your paper, you're just going to take a straight edge and you're going to make an acute angle. So acute just means it's less than 90 degrees. All right, so I made an acute angle, a little baby angle. And babies are cute. I didn't measure that angle. I didn't measure my lines. I didn't measure anything. I just made an angle. After I make my angle, I'm going to put my compass up here, and I'm going to put the needle at the vertex. Remember what the vertex is, where it comes to a point? So I'm putting my needle at the vertex. I'm going to roll it out a little past halfway on the line, or one of the lines of my angle. Doesn't matter which line. I could do it on the top one here or this. So you're putting your needle at the vertex, wheeling it out a little bit past halfway. Once you get that radius on your compass, once you get it set, you don't want to change it. You change it, it doesn't work. So get it where you like it. Go ahead and put the needle in the vertex and strike an arc across those two lines. So you're going to have something that looks like this. We still need that compass to be the same radius, so do not change anything on your compass. It doesn't work if you change it. So all I did is put my compass needle at the vertex and wheel it out a little bit over halfway across that line. Then I struck an arc. With that same radius, without changing it, I'm going to put my needle point. Now we have 2 points here. We have a point here and a point here where those intersect. So at these points, I'm going to put my needle point there, and I'm going to strike an arc on the outside. So here's my arc on the outside. You can see it. Okay. And I'm going to do the same thing on the other point. Strike another arc. And now we have an intersection. We have another point where those arcs meet. And you've probably guessed we're going to use the vertex. So remember, this was called the vertex. and the point that we just created, we're going to put our straight edge up tangent to those points. And make our line. And that line bisects that angle. So we just cut that angle into 2 equal pieces. So now this angle is equal to this angle. So we bisected an angle using a compass. So have we measured anything yet?
No.
No. We did all of this without measuring. Everybody good? Okay, now we're going to make parallel lines. And we're going to make it without using our horizontal straight edge because it would be fairly simple to use our horizontal straight edge, right? But we're going to just make a line that's a little bit at an angle, just so you can see the significance. So something like that. And then, once you make this line, I want you just to make a short line out beside it, like down below it a little bit. Something that's not too long, something like that. So we're given this line and this line. Everybody got 2 lines made? So we have the line that we're going to use, a line at some random angle, and then we have this shorter line. And I'm going to show you what that's for here in a second. All right. The next thing that you're going to do, you're going to set your compass to the distance of this shorter line. So you didn't know when you were making that line that it was going to be your given distance to make it parallel. All right. So we're going to make a line parallel to this line at this distance. So set your compass to the distance of this shorter line. Okay? Now that we have it set to the distance of the shorter line, you're going to put your needle point along this line. Now you want to put it about a third of the way up. So I'm going to put my needle point right here along that line. I'm going to strike an arc. Okay, so I made an arc. I'm moving my needle point down to about, not quite to the end, but about another third of the way up, and I'm striking another arc. So I have two arcs that started from that line. The needle point started from that line. So it's true that the radius of those arcs is equal to the length of this line. So we're making a parallel line from a given distance. And the given distance is this short line. We struck two arcs. Why did we have to do two arcs? We could actually even do more if we wanted to, but the definition of a line is the distance between 2 points. So we're going to use the tangent points of these circles to create a line. So we're going to put our straight edge tangent to the tops of those circles. Then make sure you're just touching it at the very top at just 1 point. That's what tangent means. And then we're creating a line. Once we have it lined up tangent, then we can create the line. So now we have a line that's parallel to the other line at this given distance. Okay, so line parallel to a given line at a given distance using a compass. And we could do the same thing. We're not going to do it on our paper, and just for time's sake, but we could do the same thing with two arcs. So if we had any kind of ergonomic type surface, we could make a line parallel to that surface using the same method. We would just have to strike more arcs. Okay? So give an example for that. When we reconstructed our deck a couple years ago, about 3 years ago now, we built a deck around our hot tub so we'd just be able to go out on the deck and get in the hot tub. And we wanted to put some molding around the deck opening in the hot tub just so it would look better. Well, we had to cut the molding at the same radius as the hot tub. So you can do something very similar called a scribing method, where you can outline the radius of your hot tub and mark it on your board. You just have to have a certain instrument, kind of looks like a compass, but you just roll it along the outside of your feature, whatever it is, your surface, and it marks it with a pencil on the other end on your wood on where you need to cut that. It's called a scribe, but the very same kind of concept because you're using the same radius. All right, the next thing we're going to draw is a scalene triangle. What does scalene mean?
Like no sides are equal.
No sides are equal. So we're going to put just 3 random lines here. Make one about like an inch, a little over an inch. Make another one about 3/4 of that one, and then make another one about 3/4 of your other. So basically just 3 lines, 3 different sizes. I didn't measure these, I didn't do anything with it, but we're going to use our compass to transfer those measurements. And since we're talking about transferring measurements, I'm going to show you this. You guys don't have these, but this would be an example of what it would be used for. There's things called dividers, and they have 2 needle points. So it's almost exactly like a compass without the wheel, and you have 2 needle points. So you could take this divider and extend it out to the ends of those lines. Guys, I've had enough. Stop talking over me. You could take it out to the ends of the lines, and then you could transfer that same measurement to wherever you needed it. Okay, so these were really handy when all you did was board drawing, but you can pretty much do the same thing with your compass. You don't have 2 needles. You have a lead on one side and a point on the other. But a divider has 2 points on it, and it's used to transfer measurements. So you might want to remember that. The divider is used to transfer measurements. All right, so now that we have our 3 lines, we'll start out with the biggest line first here. We're going to put our needle point on one side, our lead on the other, and just like I did with that divider, we're going to transfer this measurement. So we're just going to pick a spot that's close by, and we're going to strike an arc. Okay? And then we're going to put our needle point somewhere on that arc. Let's put it at the end point down here. So just put your needle point at the end point just to give us a reference. And we'll strike another arc. So it's going to look something like that. And just remember which point you used. I used that bottom point as my reference, that end point. So I have 2 arcs that were the distance of our largest line.
Ma'am, how do we draw these arcs?
So set your compass equal to your largest line. And then the first thing I did is draw an arc, and then I put my needle point at the end point of my arc and drew the other one on this side.
You want me to do that?
Yes, I want you to do that. Then I'm going to set my compass equal to the distance of the second line. Because what was the definition of a scalene triangle?
All the sides are not equal.
No sides are equal, no angles are equal. So if we use that same endpoint, I'm just going back to this same endpoint. I'm striking an arc. And it'll look like there's, no real rhyme or reason to this thing. But if you use your same points, then it's a little more accurate. So I used that same endpoint that I did to strike this arc. And I made another arc. And once I have that distance, I can set my needle point to the distance of the small line. And I'm going to use my other needle point. I had you strike an arc just so it would highlight your needle point there. But try to use that same needle point and strike another arc. Now, if you made your lines like way too long, like if this one is super long and these are super short, then it might not meet up. But if they were proportional, kind of like mine are, it should meet up. So now we have 3 points. We have that end point, our starting point where we had our compass, and this intersection. So if we draw a line between those 2 points, just put your straight edge tangent to those points. And you have a scalene triangle by transferring the measurements from those 3 lines. So I'm creating a scalene triangle from 3 given lines. Again, if you're using pattern development, this could help you out a whole lot knowing how to transfer those measurements like that. So we're going to make, the next thing we're going to make is equilateral triangle using our 30-60 triangle. So with your straight edge, since we're using our 30-60 triangle, we have to use our horizontal straight edge. So with your horizontal straight edge, I want you to make a line, about 1 inch or so. It doesn't have to be real big. And so here's my line. Yeah, a little over 1 inch. You can see the proportion of my line on the screen. And if we're creating an equilateral triangle, then what are all the angles going to be equal to? 60 degrees, right? Okay. So if we have a horizontal line that we made with our straight edge, we can use our 60-degree angle on our triangle, correct?
Yeah.
So we're just going to put our 60-degree angle up tangent to the endpoint and flush with our straight edge and draw a line. Okay? So the first one's going to look like this. I'm going to flip my triangle over because I need to use the 60-degree side and make it tangent to the other endpoint and make a line. So now I have an angle that's equal here, here, and here, and that angle is 60 degrees. So I put my straight edge up using my 60-degree angle, flush with my horizontal straight edge. I put it at that endpoint and made it intersected up here, so I'd have to actually erase those out to get my vertex right there. So this is creating an equilateral triangle using my 30-60 triangle. And we could do the same thing with a compass, right? How would we do that with a compass? We learned how to bisect a line, but how would we get something that's equal to the bottom line? What would we have to do in that case? Let's try it. We can make another line. Not very much, maybe a little over an inch. Mine is down here. So again, we're making an equilateral triangle. We don't necessarily have to even use our horizontal edge for this one. If we make it with a compass, then all we're doing, instead of just putting our compass a little over halfway, we have to put our compass the entire distance. So we would set our compass equal to the given line. Okay? So we're setting our compass equal to the given line. It's actual same process as if we're bisecting that line. We will put our needle point on one side, strike our arc, put the needle point on the other side, on the other end point, and strike the arc there. And instead of making the line, a bisecting line, we would just connect these points. So now we have this intersecting point, we have the points at the end of the line, and we would use our straight edge to connect those points. Now we have an equilateral triangle using a compass. Desk. We've got a few more to do today. All right, the next step is to create a hexagon. All right, so somebody tell me how many sides a hexagon has.
6.
Okay,
7.
and if it has 6 sides, then what are the angles of the corners?
30.
How do we know that?
You divide 6 from 180?
Not 180.
Oh, 360. Oh, it's 60. The angle 60.
Okay. So if we're going to use a triangle to make a hexagon, what triangle should we use?
30.
The 30-60 triangle, right? So we're going to make a hexagon in 2 ways. We're going to make one with the 30-60 triangle, and then we're going to make one with a compass. So the first one we'll go ahead and make with the 30-60 triangle. So I want you guys to use your straight edge, use your horizontal edge, and you're going to draw a line. Let's make it a little bit longer than the lines we have been drawing, because this is going to serve as a center line. And we could bisect this line, but since it's just going to serve as a center line, we don't necessarily have to bisect it because we made it with our horizontal straight edge. So what we're going to do is just use our straight edge, make sure it's flush with our horizontal edge, and we're just going to eyeball it and kind of make a center point for our hexagon. Okay? So all we did is, just make a center line so we could start our drawing. Now we're going to make this inscribe. Okay, and what did inscribe mean? Inside the circle. So what I want you to do, and everybody's circle is going to be a little bit different because you're going to base it on how big you drew your center lines. So I want you to just take your compass and,
Wait, how do you make it so straight?
well, I use my straight edge, my horizontal edge, and then the vertical line I use my straight edge off of my triangle. And I made sure it's flush to my horizontal edge. If it's not, then you're probably not going to make a great hexagon because we're going to have to use our triangles and they have to be flush against the horizontal edge. So I want you just to take your compass, and I want it to be within the center mark lines. So something like this, where we make sure that we're drawing this circle within the center marks. I mean, we could go back and make our center marks bigger if we needed to, but this is just going to help you out. So remember, compass is at a radius, so just make sure it's not going to go past, when your needle point is at that middle, make sure it's not going to go past the other side. So this might be a better indicator if you do it like this instead of putting it in the middle. So you want it just inside your center marks. And we're not measuring this distance, we're just creating it by setting our compass to what there's like a little bit less than our center mark. And we're going to start with a circle. So once you get your center mark made and you set your compass, just create a circle at that distance. And you want to keep that same radius. Well, actually, on this one it won't matter, but on the next one that we make with a compass, you want to keep the same radius. So now we have basic center mark, basic circle. You guys have done that 100 times. We're going to take our 30-60 triangle, so you're going to need that next. And the angles of this hexagon, we said were gonna be 60 degrees, right?
Yeah.
So we're gonna come off our quadrant points, which the quadrant points are these points right here where the center mark comes into the circle, right? We're gonna go off of those points. At 30 degrees. So my 30-60 triangle is up against my horizontal straight edge. And I want to line it up with my center line. So I'm making it tangent to my center line. Okay, or my center point right there. So I'm putting my 30-degree side tangent to my center point. And I'm just going to make a little notch, like a little measurement point on each side. So in the end, I have a measurement point here and here. And let me see if I can zoom in so you guys can see that a little bit better. And so I have a measurement point down here and down here. And I just did 2 of them just to save a little time. Can't hardly see this one. Then I'm going to flip my triangle over so I can use the 30 degree on that side and do the same thing on this side. I'm making it flush with my center point, and I'm just putting a little measurement point on both sides. So now I have this measurement point and this measurement point. And remember, our angle here, if I were to draw that line out, that angle was 30 degrees and 30 degrees here, so that gives me a total of 60 degrees. So now all I have to do, I have my other points because I have my quadrant points. So the points of our hexagon is a quadrant point, this measurement point, this measurement point. So we have points at the quadrants, the horizontal, or the vertical quadrants, and then those points that we made with our triangle. So now we just put our straight edge up to those points, make it tangent to the points, and that gives us a hexagon. And is this hexagon a regular polygon? Are all the sides equal? Yes. All the sides are equal. All the angles are equal. So this is making a hexagon with the 30-60 triangle. We can also make a hexagon with just our compass. And we don't actually need our horizontal straight edge for this one. I'm going to prefer that you don't have it so we can bisect a line and implement some other things that we've already learned. I'm having trouble speaking today. So I want you just to create a line with just a regular straight edge, and it's okay if it's not exactly horizontal. It's actually a little better because it shows you the difference. Is everybody with me? So once you have that line created, what you're going to do is take your compass. We're going to bisect this line. Now we've already done this, so you know how to do it. You're going to take your compass and wheel it out a little bit past halfway. And once you get your compass set, remember you want to keep it at that same radius, so don't move your wheel. We want to go ahead and put an arc with our needle on this end point. And we're going to strike an arc. And then we're just flipping our compass over using that same radius. We're putting our needle point on the other end. And we're striking an arc on that side. Now, just like we bisected the line up here, we're going to use our straight edge and connect those 2 points. And this gives us our center mark, which also gives us the quadrant of our circle. And so again, what we want to do, we don't want to go outside our center marks. So on your compass, I want you just to wheel it in within the center mark. It's for convenience, basically. This is not a geometric construction thing. It's just for convenience, so we don't have to extend our center marks out. So once you get that radius, let's go ahead and make the circle at that center point. Now, once this radius is set, once you create the radius or set your compass to the radius you want, do not change it. If you change it, it does not work. So we have a circle. Now we have a lot of lines going through and a lot of things going on. If it really confuses you, you can erase some of your bisect lines, but you don't have to. So we made our circle. We're using that same exact radius. Okay, if you've changed it, then you need to measure that radius back out. But you're going to start, really you could start anywhere you wanted to on this circle. But just for convenience sake, we'll start in this quadrant. We'll put our needle in that top quadrant. And we're just going to strike an arc around that circle. So I put my needle point at the top quadrant. I made an arc here. Everywhere I make an arc, that's the next placement for your needle point. And then you'll just strike an arc. The next arc should end up being exactly at the bottom quadrant down there, so you can kind of check yourself and make sure that you're hitting that bottom quadrant. And then you'll strike another arc, and then the last arc. So this tells us that the radius of our circle is also equal to the distance of the sides of our hexagon. because we did not change that radius. We kept the circle radius the same. And once you get all of those points, you have your top point for your quadrant and all of these arc intersections. And that allows us to put our straight edge up there and make our hexagon. So we can make a hexagon just with a compass, or we can be a little more formal and use our mechanical arm for our horizontal straight edge and make it with our 30-60 triangle. So where's some common applications you might see a hexagon used every day?
The cell phone, that's an odd one.
Let's think of manufacturing. If you're putting something together and you need anybody ever use screw threads? And you use screws to put two pieces of wood or something like that together. A lot of times your bolts have a hex head bolt. You ever heard of that? So this would be how you would lay out the head of that bolt. All right. So what is common with these two hexagons? We know we made this one with a compass. But what's common between these two besides the fact that they're just hexagons?
What's up?
Where is our construction circle?
Oh, on the inside.
The construction circle is actually on the outside, so our hexagon is on the inside. So both hexagons are what we call inscribed. So that means they are made on the inside of the circle. Okay? They're both inscribed. Now, the distance across the points is special in this case because of why? What's this distance across these opposite points? What's that equal to? The diameter, right? So you need to make a note of this. When you have the distance across the points on an inscribed circle, it's equal to the diameter. Okay? And I know that's probably hard to see there. Distance across the points is equal to the diameter. So if we're looking at where my arrows are here, so if we're given a hexagon and we're told the distance across the points and we have to recreate that hexagon, do we need to make it inscribed or circumscribed? We need to make it inscribed. We could use this same circle, or I could even draw another circle, and you guys don't have to do this, but I'm going to show you what I mean. And I'm doing this a little bit backwards because I should have made my center lines first. So we could make, using our 30-60 triangle, we could make lines tangent on all sides using our 30-60 triangle.
You can't see. Oh,
So again, you don't have to do this one, I'm just showing you the difference. So I just made a circle with center lines. I'm putting my 30-60 triangle flush against my straight edge, but I'm making it on the outside of the circle. Why am I showing you the difference here? What do you guys think? Why does it matter? I've got a rough spot on my triangle right there. Didn't want to make that line. So I'm not really measuring anything. I'm just putting my 30-60 triangle up against my horizontal straight edge and putting it tangent to the outside of this circle, but I'm still getting an accurate hexagon. But what's the difference between this hexagon and this hexagon? The circle's on the inside, right? So we would call this a circumscribed circle, or a circumscribed hexagon, which is made outside of the circle. So where is our diameter now? If I were to draw that same line across the center from one side to the other, what would our diameter be equal to now? Here it was equal to the distance across the points. What's it equal to here? The distance across the flats, right? Everybody agree with me? Our diameter is equal to the distance across the flats whenever it is circumscribed. So if I were given a dimension like this and said, okay, this is a 1.5 distance across the flats, how would I construct that hexagon in AutoCAD? What would I have to do? I don't have triangles in AutoCAD. How can I make it? We actually have a polygon command, and it's going to tell you when you click on polygon, it's going to say, where do you want to start this? So you click on the center. Then it's going to say, what's the diameter? And you would tell it what? 1.5. Okay? And then it's going to say, do you want this inscribed or circumscribed? On this case, what would we have to choose? Circumscribed. Correct? Because it's made outside of the circle. So it's not where the circle is, it's where the polygon is. This is inscribed, so the distance across the points is the diameter. This is circumscribed, distance across the flats is the diameter. Okay? You guys good with that?